What we are going to learn in this course is condensed matter physics. Now, one way to introduce this topic is to release. What is our goal? Our goal is to understand physical properties of everything that is around us. You can think of materials like a piece of metal, superconductor, insulator. You want to understand physical properties of all these materials. One way you can do this is to break down everything that exists in terms of elementary particles. And then once you know all of the elementary particles and how they interact with each other, you can build up physical properties of these systems. So here is a list of elementary particles. This is a standard model. You have 6 quarks, you have leptons, you have gauge bosons, and a scalar boson. So these are elementary particles. Why do we call them elementary particles? Is because there is something intrinsic that these particles have. All of these particles have intrinsic charge, mass, and spin associated with them. And this is their intrinsic properties. This is their fundamental property. And one way is really to break down everything in terms of this, understand all the interactions between them, and then you're done. But it's rarely that easy, because often you also encounter particles which are made up of elementary particles, but they often behave as particles themselves. For example, you can take a proton or a neutron. Now, a proton and neutron, both of them are made up of quarks. And so they're not fundamental particles. They're called composite particles. And a proton is made up of 2 up quarks and a down quark, and a neutron, 2 down quarks and an up quark. So they are composite particles made up of these elementary particles, but they still have well-defined properties like charge, mass, and spin. Proton has a charge of plus E. Mass, the mass of proton, we know it very well, and we know the spin is half. Similarly, neutron, we know the charge is 0. So we have these well-defined properties for these particles, which are composite particles. Now, this is still okay. It's small number. 3 elementary particles are involved in protons and neutrons. It turns out that if you want to really understand a condensed matter system like a piece of metal or superconductor, the number of particles that you're encountering in these materials is very large, of the order of 10 to the power 23. Now, if you want, you can break down these systems in terms of very large number of elementary particles, but this will be just impossible to track down. But how these particles combine and interact and give rise to physical properties like conductance or specific heat that we are interested in knowing. So it is a very difficult task to do it via this route. So what we will develop in this course is a new set of tools, and we'll formulate these properties of these condensed matter systems in terms of effective particles, which are particles in the spirit of particles like proton and neutron. So the effective particles in condensed matter systems will be made up of very large number of fundamental particles or elementary particles. Most of the times we'll have electron. And what makes condensed matter interesting is we know very well all of the properties of a single electron. But when we put many of them together, the system behaves in very strange ways. You can have effective particles which have mass, charge, and spin, which is very different from a single electron. You can have particles which we'll learn in this course. Some of these particles would be like a phonon or a magnon. These are really particles in condensed matter that have well-defined properties, but they are really formed in terms of elementary particles. You have really large number of electrons involved in them. Also, sometimes you have particles like Cooper pairs that we'll discuss in this course. Now, Cooper pair is really just a pair of two electrons, but in the presence of many other electrons as well. So typically, and we'll learn these particles more about them in great length at this course, but the idea is that we'll really like to understand physical properties of materials like metals, superconductors, and so on, condensed matter systems. And what we'd like to develop is a theory that allows us to describe these systems. Now, as we discussed, condensed matter systems really include many particles. So far, you've learned a lot about quantum mechanics of a single particle. So next, what we would like to do is to generalize what we have learned from quantum mechanics of single particles to quantum mechanics of many particle systems. So what we'll need to do is we'll need to make some generalizations and develop some new notation. And that is what we'll do in today's and tomorrow's lecture. And then the entire course will build upon, we'll use this notation, and it will make our life much easier. By the end of the course, we'll master some of the tricks of well-known tricks of condensed matter, and hopefully you can apply these tricks to understanding new materials that might not even exist today. But in the lab today, you can make new materials, but to calculate physical properties of these materials, you'll use the tools that we'll learn in this course. So let's start with the single particle Schrodinger equation. H psi is E psi. H, the Hamiltonian of the system, it consists of the kinetic energy and the potential energy. Now, this equation can be solved, and you can solve this equation as an eigenvalue problem. Typically, this equation admits multiple solutions. So you have many solutions of this equation, and you can label these solutions with some quantum number, say n. So this equation will typically have multiple solutions. These solutions, they're labeled, you can label them by some index n. So what I'm writing here is there are many solutions of this equation. One solution, each solution labeled by n. So for each solution, you have an eigenvalue and you have an eigenvector. This is basically the wave function describing the single particle that obeys this equation, and this is its energy eigenvalue. Now, one way to think about this wave function is to think of, so the single particle lives in the Hilbert space. Now, in the Hilbert space, you can describe the state of a system, state of a single particle, by a general ket psi. So this is just notation that you've already known. So psi n, this ket, this is a ket, this is a vector in Hilbert space that describes the state in which the single particle that obeys this equation is living. So there are n such solutions. What you can do is you can write the position representation of this ket, and this is really the wave function of the system. So this is the position ket, or bra in this case. Now, Hilbert space, so this is like an inner product. Hilbert space comes with a property which is called inner product. How is this inner product defined? Well, so to define this inner product, we simply use bracket notation. If you have a ket bra, and a bra psi m and a ket psi n, this notation is called inner product. And the way it is defined is you integrate over all space the wave functions psi m. Now this is the bra, so I take complex conjugate, and psi n r. So this is just definition of inner product. Now, the states are orthogonal if this inner product is 0. They're normalized if this inner product for same index is 1. So this you already know very well. Another thing is to consider this quantity. So some trivial remarks. H is Hermitian. All eigenvalues are real. And if you have all of the solutions of this Schrodinger equation, single particle Schrodinger equation, you can make a complete, you can make a basis set, a complete basis set, which is formed of all of the kets psi n. And then you can expand any general state in terms of this complete basis state. So this quantity psi n star r psi n r, this quantity represents the probability density of finding a single particle at r. So this is probability density of finding single particle at r. So if you multiply this probability density by an infinitesimally small volume d cube r, what you get is the probability of finding a single particle at location r, at coordinate r, within an infinitesimally small volume d cube r. Right? So this is the probability of finding a single particle at r within an infinitesimally small volume d cube r, around this r. If you integrate this, you should get 1. So this particle has to be at some coordinate. You integrate over the probability, integrate this probability over whole space, you will get 1. And this is the normalization condition. Now, as we discuss in condensed matter systems, we will deal with large number of particles. So I will typically call this as n particle system. Capital N denotes the number of particles that exist in our system. So we should extend all of this to n particle systems. Now let's do it in a very straightforward way. So for n particle systems, we'll have a n particle Schrodinger equation and so on. Let's first try to generalize these things. So imagine that you write n particle Schrodinger equation, that is the Schrodinger equation that all these n particles obey, and somehow you can solve this equation and calculate the wave function. So what will that mean? Now, the solution would really be a wave function that will be a function of now n coordinates. So you have n particles. So the solution of this n particle Schrodinger equation will be a wave function that will have n coordinates. Right? So if I write down this quantity, psi star r1 R2 Rn. This quantity, it represents some probability density. If I write down the same quantity, and now multiply this with many infinitesimally small volume elements, this quantity will give you the probability of finding one particle at coordinate r1 within an infinitesimally small volume t cube r1, second particle at r2 within an infinitesimally small volume t cube r2, and the nth particle at Rn within an infinitesimally small volume Rn around Rn. So each of these coordinates is an infinitesimally small volume around them, and this is the probability, this represents the probability of finding those particles at those coordinates. Now, what if you want to, so this is really a joint probability. It's a joint probability of finding one particle at R1, second at R2, nth at Rn. What if you're only interested in finding the probability of finding, basically calculate the probability of finding one particle at R1. So in this case, you do not care about where the other particles are. So you can have this quantity, which is, let's write it this way. So we can basically write d cube r1 and integrate all other coordinates. And so this quantity gives you the probability of finding one particle at R1 within an infinitesimally small volume d cube R1. Yes?
Right, in this notation, are the particles distinguishable or?
So we'll come to that. Actually, that's the next thing we'll talk. So now this is a very important point here, whether these particles are distinguishable or not. If these particles are distinguishable, that means if these n particles, all of them have different quantum numbers, have different masses, different charge, different spin, we don't have to do much. We can keep this notation, everything works out. But fortunately or unfortunately, in condensed matter systems, most of the times, these particles are going to be indistinguishable. Most of the times, we'll have n electrons. All of these n particles will have same charge, same mass, and same spin. Now, this leads us to an interesting fact about indistinguishable particles is that in quantum mechanics, so let's imagine a classical system. So you have n identical classical systems. Say you have n classical balls. They have same shape, same mass, same density, everything identical. You can describe this system by putting a mark on each of these balls and then follow their trajectory. So you can label this particle is 1, this is 2, this is 3, and you can follow their trajectory in phase space. In quantum mechanics, you simply cannot mark a system, mark an object without disturbing the state it is in. So you simply cannot put a mark on an object. So this is a fundamental assumption that we are going to make, that n identical particles in quantum mechanics, they are indistinguishable, right? So if these n particles are indistinguishable, as she asked, that means that has a very important consequence for this object, this wave function. Some of them we'll discuss now, and some of them you will do a problem in the tutorial and you'll learn more about them. So one way to think about this is consider this wave function. So let me just write down this object once here. So this is a wave function of n particles. Next, what we like to do is we like to think of an imaginary process where we are exchanging two, and so for the moment, these are all identical particles. And what we want to do is we want to exchange two particles, say the jth one and the kth one. So if we exchange the two particles, we still have n identical particles, but their coordinates have now been interchanged. So the physical state that is represented by the wave function must remain same. So if we exchange two coordinates, at most what can happen is this wave function gets multiplied by a complex scalar. If you exchange it again, you'll get again the same prefactor. So we can write this as psi, say R1, Rj, Rk, Rn. Let's exchange j and k. This is simply going to give us R1, Rk, Rj, and Rn. Now, let's exchange them again. So, for what we just discussed, if we exchange these particles, these are n particles. At most, if we exchange this, what can happen is this can become some complex lambda. So, okay, let me write it this way. Let's exchange this j and k. So we'll get this quantity rk and rj. And at most, you can get a multiplicative factor lambda, which is just a complex number. Now, in this rk, rj, so I have these two coordinates location. I've exchanged them. At most, I can get, so let's think of a dynamic process. So you start with this n particles, you exchange these two, and you get this factor lambda. And then you exchange them again. Then you will get lambda square. And now all of the particles are back in the same order. You have R1, Rj, Rk, Rn. So this lambda, let's say it's a complex number. You can write it as e to the power I5. Why can we do this? Because we know if we exchange it twice, we get back to this. So lambda square should be 1. So what this means is lambda square is 1. So we can write down lambda as, so it's a complex number with mod 1. So lambda can be written as e to the power I5. So now exchanging two particle once and exchanging the particle twice, this can be thought of as a dynamic process. What I mean by that is you can think of these n particles at n different coordinates, and you're really moving one particle around, you're exchanging the particles in real space. So if one particle here, one particle here, you want to exchange them. Yes?
Sorry, is lambda squared equal to 1 or modulus of lambda squared equal to 1?
So lambda square modulus is 1. So what that means is this lambda square should be 1. Yeah. So
the complex modulus or the lambda itself as a complex number?
So lambda is a complex number, and yeah, so let me write it this. Lambda is, the modulus of this is 1. So, yeah.
But why do you get lambda for one interchange?
So this is the most general thing. At most, that can happen.
Like for one interchange, you get lambda, and for the other one, you get lambda.
So now I'm doing, so one interchange, I get lambda, and now I'm doing this again. So I get another lambda, so I'm just writing it as lambda squared.
Yeah, but that's different from mod lambda squared.
Sorry?
But that's different from mod lambda squared, right?
Yeah, so we'll see. So this assumption, now we are assuming that now we are back in space. So this has an important consequence, which you will deal with in the tutorial. So now we are going to assume that here we are back to the same state, this. This is as if nothing happened, right? So if nothing happened, then lambda square, this should really be a trivial factor. Yeah?
Sorry,
Yeah.
it's a mathematical question because the solution lambda, modulus of lambda squared equals 1 and just lambda squared equals 1 have two very different sets of solutions. One is a general phase, the other one just has a solution plus minus 1.
So right now, we'll start with lambda squared equal to 1, and then we'll divide this into different cases in 3 dimensions, 2 dimensions, and 1 dimensions. And in all of these dimensions, we'll see that what you're pointing out actually gives rise to something called anyons. And this will be discussed in the tutorial. So we'll just discuss it now. So as he pointed out, this is really a complex number and it has very different sets of solutions. And this has very important consequence for what kind of particles we really have. Now, you can think of exchanging these particles as really moving these particles around in space. Now, what you care about is the final coordinates of these systems. So, in what way you're exchanging these particles or moving around really doesn't matter. So, this phase that you will get once you exchange the particles, it should not depend on the precise path that you exchange the particles in. So what you should really think about is the number, or is topologically distinct ways of moving particles around each other. Now, if you take the case of 1 dimensions, you have 2 particles, say there are n particles total. I'm just showing 2 of them, particle J and particle K. You simply cannot exchange them without them colliding. So we are assuming in this dynamic process that we are moving these particles around when we exchange them, but there is a constraint that these particles must not collide with each other. In 1D, you simply cannot exchange them. And this has an important consequence, and you might have heard in 1D, some people say that bosons and fermions are same, or bosonic fields, fermionic fields are similar, and this is precisely related to this. The fact that you simply cannot exchange 2 particles in 1 dimension. Now, it turns out in 3 dimensions and higher, you can exchange particles. There is a huge phase space available to you. You can exchange particle J around K. So let me try to do this in 3 dimensions. So say I have particle in this plane, another particle here. Exchanging the particles twice is like moving this particle around this particle and back here. In 3 dimensions, what I can do is I can contract this loop continuously. I go a bit above, shrink it to 0. So in 3 dimensions or higher, all of the paths that you use to exchange can be shrunk to a single point. What this implies is that in 3 dimensions, all you can have is, so actually let me omit this mod lambda equal to 1 because it costs some, let's forget that. Let's just keep some complex number e to power I phi. Now, in 3 dimensions, because all of these paths are basically shrunk to 0, which is same as not doing anything at all. Now, in this case, we are sure that this lambda square should be 1. So in this case, 3 dimensions higher, when you're doing nothing at all, lambda square is 1. That means e to the power 2I phi is equal to 1. That implies that phi is either 0 or either pi. Now, phi equal to 0, it's for particles that we call bosons, and phi equal to pi is for particles that we call fermions. So we have n identical particles. When we exchange them in 3 dimensions or higher, there are only 2 possible solutions, phi equal to 0 and phi equal to pi. Phi equal to 0 corresponds to bosons, and phi equal to pi corresponds to fermions. So let's just write it down, what that means for us. So if you have psi R1, Rj, Rk, Rn. Now this, if we exchange particles, what we are going to get is psi R1, Rk, Rj, Rn. Now for bosons, you will have plus sign here, and for fermions, you will have minus sign here. So this is equal to this. This is for bosons. This is for fermions. Now, let me extend this trivial thought experiment in 2D. So we did 1D, no exchange, 3D, trivial solutions, which are bosons and fermions. In the tutorial today, you will discuss one particular case for 2D. If I just do this exercise, 2D, try to move this around. Now let's try to shrink it to 0. You can't shrink it to 0. You can't shrink this path without colliding with this particle, right? This has very important consequence. Why? This would mean now you will solve again this equation to find out what solutions it admits. You'll find that phi, there are solutions when phi is not equal to 0 or pi. And these solutions correspond to particles which are called anyons. So they are not bosons or fermions, and they can exist in 2 dimensions, and you will do this in detail in the tutorial today. So for now, let's deal with the simple case of bosons and fermions. Yes?
If we have a topological defect in 3D, is it possible to have anyons?
Yeah, so there are, so what we are doing is very formal at the moment. Then you can think about like what you said, some topological defects, or also some systems which are 3D, but they're effectively 2D, as in there is some topological constraint. So sometimes you have a system that is 3D, but there is some topological constraint that gives, that constraints, that means that there is some surface state. And because the surface is 2D, then you can have these anyons there also. So you can have some exotic system where you, so, but formally, let me state, this is just a formal solution of this lambda, this exchange phase, right? Formally in 3D, you can only have 2. You will have to be more creative to get anyons in 3D. Any other questions? So now let's just derive another trivial thing that we know. I'm going to go back to 3D and stick to bosons and fermions. Now let's consider two fermions. So you have psi, one fermion is at R1, other one is at R2. And if we apply this exchange, this should be equal to psi R2, R1 with a minus sign, right? Now, what if you have both particles at the same coordinate R? That would imply that psi R is equal to now if you exchange them, you'll get psi minus psi R. It simply implies that psi R is 0. This is what is called Pauli's exclusion principle. You cannot have two fermions at the same position R. Now, there is nothing special about the position representation we have used in discussing this exchange. You can do this exchange also in momentum representation. So you can generalize this statement that two fermions cannot be in the same quantum state. It simply follows from this exchange. This we have done in position representation. You can do it in any other representation. And this is the Pauli's exclusion principle. Now, for bosons, this does not happen. For bosons, you can have two particles at same coordinate and by extension, two particles in the same state. And this has important consequences, which you might have learned in StatMech course. This leads to Bose-Einstein condensation. What that means is at low temperature, you have many bosons, identical bosons. They will minimize their free energy by occupying the same quantum state. Because they can occupy the same quantum state, they are not forbidden by any exclusion principle, and this leads to formation of a condensate. Later on in this course, we'll discuss the phenomena of superconductivity, and we'll discuss in detail. There is a similar condensation that goes on, condensation of Cooper pairs. And so we start with fermions, pair them, make bosons, and these bosons then form a condensate. But we'll do it in great length later on in the course. So for now, we'll write down two simple equations. Or we'll just keep in mind fermions are anti-symmetric. Under exchange, what I mean is psi R1, R2 is minus psi R2, R1, and bosons are symmetric. So, any questions so far? So next, what we are going to do is we are going to assume that we have n particle system, n identical particles. But so these n particles, they are all, let's assume some fundamental particles, say electrons. Now they can interact with each other and make the system very complicated. But for the moment, let's assume that these n particles are not interacting at all. That means you have n copies of a single particle that obeys single particle Schroedinger equation. And let's assume that the single particle Schroedinger equation we can solve and we can find all the eigenstates of this single particle Schroedinger equation. No interactions, non-interacting system. We can find all the eigenstates of single particle. And now what we would like to do is we'll like to write this wave function for n, this wave function for n particles in terms of single particle states. The goal here where we are headed is we would like to, so for single particle Hilbert space, we have a complete basis, that is all the solutions of the Schroedinger equation. What we would like to do is to form a complete basis for n particle Hilbert space. That is our goal. So how can we write an n particle state? Provided we know all the single particle states. That's what we're going to do next. So say you have solved that equation and the solutions are labeled with some quantum number that, so we can solve this single particle equation and all of the solutions are labeled by psi k1. Let's use the notation R1, then K2, R2. So this is a set which contains all of the solutions that the single particle Schroedinger equation admits, and these solutions are labeled by K1, K2, and so on. From this complete set, let us choose capital N states. Okay, so now this is a set which has finite Kn elements, and these are n, capital N, single particle eigenstates. Now, one way you can write down a n particle wave function psi R1, R2 to Rn. One way you can write down this wave function is to think that, okay, this is really a system of non-interacting particles, so I can just write down this wave function as I can separate the variables and write down this wave function as a product state. So what that will mean is you write this n particle wave function as a product of K1 R1 psi K2 R2 psi Kn Rn. Now this is perfectly valid n particle wave function. There's nothing wrong with it, but it's not very enlightening in the sense that if we think about exchanging two coordinates or two particles in this n particle system, let's say you want to exchange 1 and 2, in this product state, the one particle always comes with quantum number K1. If you exchange, R1 comes with quantum number K2, R2 has quantum number K1. So you would like to formulate the n particle wave function by treating all the coordinates on equal footing. So all of these quantum numbers K1, K2, Kn should have a term where in that term they have the coordinate Ri. This will lead us to defining what is called Slater determinant or a permanent for a boson. So essentially what we want to do is we want to develop a notation which encodes the fundamental exchange symmetry for bosons and fermions built in or implicitly in the notation. So we'd like to treat all of these coordinates on equal footing. so that K1, so there is this term in the wave function, but then there is another term in the wave function that has coordinate R2 coming with quantum number K1, another term that has coordinate R3 coming with K1, another term with R4, and so on. This can be done. So this, let me write down, simplify the notation. This I'm just going to write as a product state over Ki psi Ki R. So we can, one way we can treat all coordinates on equal footing is to apply what is called a symmetrization and anti-symmetrization operator. I'm denoting it by S plus minus. This acting on the product state, let me change notation, just let's call it J. So J varies from 1 to capital N. This psi Kj Rj. What this symmetrization operator does is the following. This is equal to 1 over n factorial. And let me write it down and then I'll tell you what I mean by it. So you have psi K1 R1 and then you have psi K1 R2 till psi K1 Rn. Then you have the second row where you have psi K2 with argument R1, psi K2 with argument R2, then you have psi K2 with argument Rn, and then you have psi Kn with argument R1. Psi Kn with argument R2 and psi Kn with argument Rn. So I'm going to write down this something here plus and minus, and now I will explain what this is. If you have fermions, then what you have is a regular determinant, and it is called Slater determinant. Now, so this is what the symmetrization operator does. If you have plus or minus, we have this plus or minus here. If we have fermions, we'll have S minus. And when you have minus here, this is just an ordinary determinant. How many terms are there in this expression? Well, let's calculate how many terms are in this determinant. So you can take the first row, you can just expand the determinant, remove this, and you have another determinant of this. So corresponding to this term, you will have another determinant here, then you'll have this term with a minus sign, and then a determinant formed by removing this row and this column, and so on. So you always have this alternating plus minus signs in regular determinants. That's what is implied by this minus sign. For bosons, all of these signs, if you replace them by plus, this is what is called a permanent in the formal definition. So that's what I really mean by this plus. Any questions so far? So if you expand this determinant, assuming fermions, you will see that the total number of terms is n factorial. So if you expand this, you will get one term from this, then omit this row, this column, determinant here, and then this, so n terms from this column, and then you'll realize that this determinant itself is n minus 1 terms, so you get n times n minus 1, and then in that term you'll have n minus 2 terms. Total number of terms is going to be n factorial. This is just a normalization factor. I think this is also part of the tutorial today. You will show that this capital N factorial with square root is simply a normalization for this n particle state, normalization factor.
And what if you have a system where you have fermions and bosons?
So you will typically split them, treat n identical bosons separately. So you'll start with this quantity and write this as direct product of two wave functions, assuming that these fermions and bosons are not interacting to different Hilbert space, and then do the same thing. So that becomes tricky because part of it will be determinant, part of it will be permanent.
And you have also to do the permutations, right? To have first
Yes.
all the bosons and then all the fermions.
Yeah. So let's stick to this case. So what you're saying is typically happens in systems. So next, after this, we'll develop another set of notations where we'll do all of this in terms of operators. That is called the second quantized notation. So right now we are still dealing with wave functions. The first quantized notation will build another set of tools using second quantizations where we'll deal with operators. And in that case, this exchange of particles, this plus minus signs, will be encoded in commutators or anti-commutators. And that makes it a bit easier to deal with a system where you have same species, or it makes the calculations are easier to do using that notation.
What would happen if you have anions?
Sorry?
What would happen if we have anions in this case?
So if you have anions, then the exchange state is, so typically you can write this, but here there are so many other phases involved that it's let's say it's not very useful way of writing it. So when you have anions involved, you would like to develop what is called braiding statistics. So in the case of anions, as we discussed, you cannot shrink you think about topologically distinct paths that you can exchange them. And then what you will arrive at is what is called braiding statistics. So really moving around these anions, and you have to remember which one was exchanged first, which one exchanged other. And by remembering them, you will take into account all the different phases, which are different from plus and minus. So it is, in short, it is messier, but there is a way to track them by using a different formalism where you think about braiding statistics of anions. So far, this is a way. So let's talk about permutations that you were mentioning. So this determinant for fermions or permanent for bosons has n factorial terms, and all of these terms can be obtained starting from this term. So this is really a term that has on the diagonal R2. So if you start with this term, you can obtain any term in this determinant or permanent by a permutation of this term. So you can change R1 by permutation. I mean, replace this argument by something different, exchange R1, R2, and then. So each term can be obtained by many permutations of this term. If the number of permutations required is even, you will have plus sign with that term. If the number of permutations required is odd, you will have a minus sign with that term. So this is just a fancy way of writing down a general expression of a determinant. So this is just nothing but definition of determinant. Depending on the permutations, you get, if it's even, you get plus sign, odd, you get a minus sign. And for the object called permanent, independent of even or odd permutation, you always get the plus sign. So far, this is one. Okay. So we have written down an n particle wave function in a way that encodes the exchange symmetry. So far, this is one state with one set of quantum numbers k1, k2 to kn. Next, so this is just one ket, so to speak. So if you think of n particle Hilbert space, this object, this determinant or permanent, this is one ket in the n particle Hilbert space. What we would like to do is to write down a complete basis of this n particle Hilbert space. We can do that by allowing all possible values for K1, all possible values for K2, all possible values for Kn. So if all of these quantum numbers are allowed to have any possible value, which we obtain by solving the single particle Schrodinger equation, we can generate a complete basis set for n particle Hilbert space in terms of non-interacting particles. Now this is quite useful, at least to think, not useful in practice. So if you have an interacting system, in principle, if you have a complete set, you can expand any general state in terms of this complete set, right? So I can write any n particle wave function, R1, R2, Rn. This is now a general ket in n particle Hilbert space. What this ket represents might be a strongly correlated system, any complex object, some general n particle ket. In principle, I can write it down as, now let me write down the expression. So this is some normalization factor. Let me just denote by this n, sum over all quantum numbers K1, K2, Kn, some coefficient, I call it alpha, K1, K2, Kn, times single ket K1, K2, Kn. So what I mean by this object is this K1 to Kn. For fermions, it is just this determinant. For bosons, it's a permanent. So there are many notations. This is a general ket without any k's. When I write down with these k's, I mean one ket written down like a determinant or a permanent, and then I allow for all possible values of these quantum numbers. For each such term, I have some coefficient. I sum over all of them. In principle, any general state can be written down like this. So now one would say, well, okay, if we can solve single particle Schrodinger equation, in principle, we can do everything, deal with all the interactions in this basis set. Now that is true, but for practical cases, it turns out this is not as useful. But this is very useful as a thought process that you can, in principle, do this. Yes?
Sorry, you say this can describe even interacting?
Yes. So all I'm saying is a mathematical statement. I have a complete set, a basis set which is complete for this n particle Hilbert space. Any state, any general state in this n particle Hilbert space can be written down in terms of this. But finding these coefficients, yes?
But won't the Hilbert space be, like, when they're interacting, that will change the potential?
Yeah, it will change the potential, and when you would, it's a very complicated problem, and this change of potential would make calculating these coefficients ridiculously hard. So we'll encounter some cases when we discuss superconductivity. For example, write down the n particle solution. Try to see if we can calculate these 10 to the power 23 coefficients, and we'll give up very soon.
Yeah, but I'm not sure I even understand why it's mathematically possible. Like, so it's will the Hilbert space be the same regardless of?
So the Hilbert space so far, and we are just saying we have one particle, single particle. Yes. So the Hilbert space, this is maybe if you have interactions, strong interactions, you need not think. So okay, first the space that we are talking about here is n particle Hilbert space. This can be huge. Now, for some specific interactions, you can discard many sectors of this huge space and deal with a smaller one. What we have describing here is, in principle, a complete set for this larger Hilbert space. Does that help? But I mean, again, just because we can write it down won't really help us in practice. And I think what maybe one direction that your question points to, sometimes there are, like what she was mentioning also, there are really phenomena called like phase transformations. Are you implying? So sometimes it can happen that the whole system changes. Now, in that case, the Hilbert space will be, for example, it might be possible. So we are assuming that nothing like that is happening. So you start with n particles. The potential, interaction potential can be very strong, can be very weak, but we still start with n particle systems and they remain n particles. It's not that some particles are created from vacuum, like all these things, exotic, let's say, for lack of a better word, these exotic phenomena we are omitting for the moment. But if that happens, then we are in trouble. So this is perfectly valid way of describing n-particle quantum system, but it's not very useful. So next, what we would like to do is go to second quantization. Which is a way of simplifying this notation so that we don't have to deal with these n wave functions and single particle wave functions, but all we keep track of is whether these single particle states, they're occupied or not occupied. So second quantization is basically a formulation of n-particle quantum mechanics in terms of occupation number of single particle states. So how can we go to this occupation number representation? It's a two-step process. Step one, we have already discussed this. We solve the single particle Schrodinger equation and we calculate all the possible states of this single particle, and we have a complete set. Let's write down this set. So we just write down as choose a complete single particle basis set. So for notation, let's write it as nu1, nu2. These are just some kets. So this is kets. These are first quantization. These are just wave functions, all the wave functions. Now we think about all the kets that are solution of single particle Schrodinger equation. And step two is to formulate a representation where we only count how many particles are there in each of these states. So a typical state in occupation number representation would be a ket like N1, N2, so what this ket is its numbers. These are numbers here, N1, N2, integers. 0, 1, and so on. What it tells you is how many particles are there in these sets, and the order is same as the one we choose in step 1. So we give the occupation numbers in the same order. So this can be a very large set. If you have, say, capital N particles, that means a lot of these numbers will be 0. If you have capital N particles, for bosons, you can even have many particles in the same ket. So you can convince yourselves that these are all numbers. Many of them will be 0, and sum over all of them should give you the total number of particles, n. Right? So let's try to think a bit more about what this notation really means. Let's start with vacuum, that there is no particle at all. So you have a set, or you've solved the single particle Schroedinger equation, you have all the kets that form a complete basis. Vacuum simply means a ket that has no particle anywhere. This simply vacuum. This is one ket like this. Then you have many other kets. You can have like one particle in the first one. You can have 0, 1. And so on. So you have many states in occupation number representation like this. For fermions, you can only have 0 and 1. For bosons, you can have more than one occupancy also. Now, the space spanned by all of these kets is called Fock space, denoted by this F. This is the space spanned by all of these kets, all of these occupation number kets. Any questions so far? Yes.
What are the occupation numbers for anions?
So for anions, again, well, we'll say, so it's slightly more complicated. It's useful. One way to think of is if you are, so far we don't know any fundamental particles that are anions. So typically we think about anions that are formed of fundamental particles like electrons, fermions, regular fermions. So in that case, for an anion to be occupied, you know that the fermion should be occupied, and then break down this fermionic occupation into anionic occupation. So you can have a theory, if you don't consider anions as fundamental particles, you can formulate a theory where occupation numbers are only for bosons and fermions, and that will lead to anions. Now, who knows, maybe there are, I don't know of any proof so far if there cannot be an anion as a fundamental particle, but this would be a very strong, I'll be surprised, but maybe let's assume there is. Let's imagine that you want to make in that case, again, occupation number, this notation of occupation number representation would not be a good representation simply because you will be dealing with annihilating. So in that case, it would be more useful to think about operators that create an anion, but don't give you one there. So if you think about creating a particle here, if you create a fermion, you can go from this state to this state by acting the creation operator. You can annihilate one particle here, go to here. So this is very useful representation for fermions and bosons. But this would no longer be true for anions, but these operators still remain very useful. So you will still keep the vacuum, and you will have a string of operators here that will be creating anions, and then every time you braid, you will move these string of operators, and you keep in mind what these string of operators are manipulated. So in that sense, this representation might not be as useful for anyons, but you can still, there will be some merit to doing this. To at least you can start from here and see how complicated the problem is for anyons. Okay, so we've already discussed these basis states, some trivial facts. These states M1, M2, N1, N2, these will be orthonormal. So now this is property of Fock space. So in the second quantized or occupation number representation, you have delta functions M1, N1, M2, N2, and so on. So starting from vacuum, you can go to, so these are many states in this. So this is our occupation number representation. If you allow for all possible occupations, you'll have a complete basis. Complete basis, all these states which have occupation number of all of these single particle states, if you write down all the possible occupation numbers, that forms a complete basis. Now, this is the idea of second quantization. This is a complete basis, finding all these alphas, but also there will be coefficients in front of these kets if you expand a general set. But the main idea is by giving the occupation numbers of all of these states, you can generate a complete basis which consists of kets like these. And there will be many kets like these. These kets are connected to each other by action of creation or annihilation operators. So let's do this simply for bosons first. They're easier to handle. So what we can do is we can define creation and annihilation operators for bosons. So let's deal with bosons first. So I will use operators B's for bosons and C's for fermions. A creation operator acting on Bj dagger, acting on a state in this representation. This is with index J, and let's assume that the state has occupation number Nj. This is simply square root Nj plus 1 and similarly you can define the annihilation operator J acting on this state Nj. This gives the factor square root Nj. And now you have Nj minus 1. Now the choice of these factors, square root Nj plus 1 and Nj, they are chosen such that if you have annihilation operator acting on vacuum, you get 0. And if you have creation operator acting on is no particle in jth state, so it's not true vacuum, so there's no particle in 0th state, this should give you one particle in jth state. So this is just some definitions. So next what we can do is we have defined now operators, some new objects. These operators, creation and annihilation operators that create and annihilate bosons, and they act on this new kets that we discussed in occupation number representation that span the Fock space. Their action is given by those equations. Next, what we want to do is we can derive commutation relation for these operators. This I think you've already done multiple times for single particles. So it's a straightforward generalization to this notation with n particles. This acting on nj. This you can calculate. It's pj dagger minus pj dagger pj acting on this state. And you can see that this, using those equations, this you will find it to be 1 times the state. So what you've done is you've derived this commutation relations between these objects. pj dagger is simply 1. Now, because you have many single particle states denoted by this index j, so you have many pairs of creation and annihilation operators. And these many pairs, they have this commutation relations given by this formula. So what I mean by that is I can generalize this and I can write down a more general version of this in the following way. And you can derive this using the definition of these creation and annihilation operators. So let me write down the general commutators once. So these operators bj and bk, for different indices, they commute. pj dagger, pk dagger, they commute. And commutator of pj, pk dagger, this is simply a delta function. A crucial point is to remember that the order of operators is very important. One way to think about exchange, so for bosons, it's not as important because you don't have the minus signs when you exchange the particles. One way to exchange particles is to act with creation operators in reverse order. So you create jth particle first, and then you create kth particle. That means the jth particle is created at R1, kth particle is created at R2, or you can reverse the order and create the kth particle at R1 and jth particle at R2. Now, we can also define something called the number operator. So this number operator, let's define for the state, the index j. Corresponding to index j, the number operator is defined as bj dagger bj. This number operator acting on this state nj will give you the occupation number nj times the state. So the eigenvalues of the occupation number operator are simply the occupation numbers. So these eigenvalues nj's that appear in this ket, they must be, because these are just numbers, they must be non-negative integers. Now, how will you create this state from vacuum? You can create this state from vacuum by acting with the creation operator nj times. bj dagger, just act nj times on. So starting with 0 particle in the jth state, all other states can have any other occupation number. You can act with the creation operator nj times to get this state. But now we have to account for those square root factors. So what you will get is a square root nj factorial here. So generalizing this, you can create n1, n2, this as E1 dagger N1 So starting from vacuum, you can generate all of the kets in this complete basis in the occupation number representation by acting with the creation operators corresponding to them. Any questions so far? Now for bosons, this order, if you exchange them or move them around, you don't get any additional sign. That is encoded in these commutation relations. Now for fermions, you don't, any questions so far? So far we have done bosons starting from vacuum, how we can create a representation in terms of occupation number by starting from vacuum and creating particles. You can create a complete basis set in this occupation number representation. You can do the same thing for fermions. So for fermions, all of these, now for, let's say, fermions, for fermions, everything will follow almost identically, but instead of commutators, you'll have anti-commutators. So you will have, so you can define creation operators, Cj dagger and Cj's. And these creation and annihilation operators, they will have anti-commutators. Which is defined as Cj, Ck dagger plus Ck dagger Cj. This is equal to delta Jk. And then the anti-commutators of Cj, Ck is 0, and anti-commutator of Cj dagger, Ck dagger is 0. Again, all you have to do is to use those definitions and know that for fermions, you can, the occupation number can at most be 1. This you can also see because these anti-commutation relations are really derived from fermionic operators. You can simply see it here. If I write down this dagger one, I have Cj dagger, Ck dagger plus Ck dagger, Cj dagger is equal to 0. If j is equal to k, that really implies that Cj dagger square is 0. Now what this really means is that the single state denoted by the index j can at most have 1 fermion. If you try to create 2 fermions, you'll get 0. And this is again restating the Pauli's exclusion principle. Any questions so far? So for bosons, you can have multiple occupancy, but for fermions, you can only at most have 1 fermion in the state, and that simplifies the Hilbert space. It reduces it a bit, but it complicates the calculation because now you get minus sign. So actually, in the end, typically we'll have problems with if we're dealing with fermions. So the Hilbert space is slightly reduced. We can see this reduction or reduced Hilbert space by following. So if you start in 0j state, a state with 0 fermion, if you act with Cj dagger and you create 1 particle in this jth state, if you act with Cj on this state, you get back to 0, right? If you act with Cj dagger here, you'll see you will get nothing And if you act with Cj here, you'll get nothing. So starting from vacuum, you can create one particle, and then, so if you are dealing with these creation and annihilation operators for fermions, only for each jth state, the Hilbert space is actually two-dimensional. The only occupation number 0 and occupation number 1 are allowed. But in general, you have n particles, so it's really 2 to the power n. For each particle, you have a two-dimensional space, whether it's occupied or empty. Now, for bosons, it's not two-dimensional. You can keep acting with these daggers. There is no limitation. So typically, you will have very large, depending on where you want to terminate the basis set. In principle, you can have infinite particles in the same state. So next, what we would like to do is we'd like to relate this notation with those determinants. Now, this is a bit tedious exercise, so we want to do that in detail. So for the moment, let's extend. We have this creation and annihilation operators. We can also define number operators for fermions. It's Cj dagger Cj. So I'm just restating this thing in terms of equations. So you have Nj operator acting on 0j. This is simply Cj dagger Cj acting on vacuum 0. This has to be 0 because destruction operator. Then you have Nj acting on 1j. This is what. Now, what is one particle in jth state? That means really, so Nj is Cj dagger Cj. 1 in j can be written as creating one particle in vacuum. Now this, again, you can write, I can write this as 1 minus Cj dagger 0. Now this, the second term, Cj dagger square, gives us 0. So this is simply 1 times 1j. So this number operator can at most have can only have two eigenvalues, 0 and 1. So the next exercise we want to do is to relate the occupation number representation with those symmetrized or anti-symmetrized product states of n single particle wave functions. And we can do that by relating the basis states of each version. So let's do this in detail tomorrow. So tomorrow we'll start with this. We have learned some basic notation. We'll take it further tomorrow and then try to write down Hamiltonian for a general system which includes two particle interactions in terms of these notations.